There is a classic set of problems in physics called the projectile motion problems. And the name is fairly self-explanatory here. We have some kind of a projectile. Maybe it's a cannonball or something. Maybe it's a gun firing a bullet. And if we draw the graph here, we have some kind of a projectile shooter. In this case, maybe some kind of a cannon, a gun. We don't really know. And we have a distance axis here, a height axis for how far up we're going. And we have our projectile here, and it's going to have some kind of starting velocity for how far up it's going, how far it's going to the right, and we're going to have some gravity that is always pulling us downwards, and finally we're going to have some angle that we are firing up from the ground from. Maybe we're firing nearly straight up, maybe we're firing very close to the ground. And given this, projectile motion asks, what will the trajectory of the projectile be? What is the trajectory? And also, how far down are we going to hit? What is the distance from where we fired? A common question you might see is where you know the velocity, gravity, and distance. So, for example, you know that the cannonball comes out. I'll do it in the same yellow. You know the cannonball comes out of your cannon at 10 meters per second. You know that gravity is going to be pulling it down at 9.81 meters per second squared towards the ground, so negative. And you know that you want to go 100 meters forward. Given these three pieces of information, you might ask, what is the angle I should shoot at? Should I shoot my cannonball 10 degrees up? Should I shoot my cannonball 20 degrees up? Maybe, is it even possible to go 100 meters if you're only shooting 10 meters per second out? Maybe it isn't. Well, projectile motion is the math that can solve this problem. So let's start by writing out some equations here that we know we'll have. Let's start by writing out our velocity. We're going to have two different velocity functions because velocity is a vector. So we're going to have our x velocity, v sub x, and we're going to have a y velocity, v sub y. And if we draw ourselves a right triangle here representing velocity here, the hypotenuse velocity, and then we have our angle, theta, for how far off we're coming from the ground. And the question is, what are these components of the triangle? What are the legs? Well, as we know, the bottom is going to be the cosine of theta times velocity, v cosine of theta, and the y component here, the upper leg, is going to be v sine of theta. And in the x component's case, there's nothing to drag x. We're ignoring air resistance here because typically it's negligible. So for the entire length of this projectile's flight, the x component of the velocity will just be v times the cosine of theta. Alright, but the y component is slightly trickier. At the beginning of the flight, the y component will be v, not v cosine, but v sine of theta. But as the projectile goes along, every second that it goes along, it's going to be pulled down negative 9.81 meters per second squared, right? So we have to subtract out this gravity times how much time that gravity has had to act. How strong is the gravity? How long has it been acting? This is on the velocity. Alright, so now we have the x and y components of the velocity. Now what we can do is we can integrate this to get the position. Because remember, we care about the position more than the velocity. We're ultimately trying to figure out when this projectile is going to get to our distance here of 100 meters, and given when it's going to get there, given our angle, what the angle should be so that we do hit 100 meters. All right, so how are we going to integrate this? Well, we know, again, our position functions are going to each have, they're going to have two components, right? The x component, the y component. And the x component of the position vector, px, is going to be, again, a function of t. And this is just going to be the integral from 0 to t of the x velocity given t dt. So what is this? Well, if we integrate the x velocity here, we get v cosine of theta dt goes to v cosine of theta times t, because we have no t's. This is like a constant that we're integrating here, plus c. And of course, though, we know that there is no constant of integration here because the entire time we're just going v cosine of t. We're assuming that we're starting at 0. And if we're starting at 0, then we don't need to worry about this constant of integration. So we'll get rid of it. We know we don't need it. And from 0 to t, we're just going to get t here. All right, let's do the y. So the y component of the position vector, again, a function of t, this is going to be the integral from 0 to t of vy of t dt. And what is this going to be? Well, we have two terms now. So we're going to have, again, v sine of theta. This looks like a constant. So we're just going to get v sine of theta times t. And then minus gt. This here is going to turn into, minus gt is going to be minus gt squared over 2. T squared over 2. Right? Because when we take the derivative of this, the 2 comes down, cancels out the 2, and then we just get minus gt. So these are our two position functions. V cosine of theta t, that's the x component, which makes sense. We're linearly going forward. And then we have this y here, v sine of theta t minus gt squared over 2. And again, we could say plus a constant of integration, but we're assuming we're starting on the ground, so we don't need this t, or this constant of integration in this case. And now what we can do is we can look. This is a parabola. It's some kind of a quadratic. We can say, what is the root of this quadratic? Obviously, one root is going to be at 0, 0. This is where we're beginning our flight. But the other root is going to be here at the end when we crash into the ground. And we're going to figure out this root, and we're going to set it equal to d, and then solve for theta. That's the plan. Okay. So we know that we have our y position function. So let's just write it out one more time. We can organize it up. So we have negative gt squared over 2 plus v sine of theta times t. We're setting this equal to 0. And if we set this equal to 0, well, we can do some factoring here. So we can take the t out, and you get negative gt over 2 plus v sine of theta equals 0. So we have either that t equals 0, or we have the second option. This is the option that we want. This is where negative gt over 2 plus v sine of theta equals 0. And what is t in this case? Well, we can subtract v sine of theta. So we have negative gt over 2 equals negative v sine of theta. And then we can multiply by 2 and divide by negative g. And we get that t equals, so we're multiplying by, so first of all, we're getting rid of these negatives here. And then we're multiplying by 2, so we have 2v sine of theta. And then we're dividing by g, divided by g. And this here, this is what we care about. This is the t where we're crashing into the ground. This is when the y equals 0 for the second time. So this is important to us. But of course, we remember, this is just the time. We're looking for what the x-coordinate is going to be, what the distance is going to be at this time. And to get that, we're going to need to plug this in to our p of x of t. So the x position at t, where t equals 2v sine of theta divided by g. This is going to be the x position when we crash into the ground the second time. And if we just plug this in, we're just multiplying v cosine of theta by this quantity, 2v sine of theta divided by g. All right, so let's look at this here. If we multiply this all through, we're going to get v squared, because we have two v's, times 2 cosine of theta sine of theta divided by g. And we can use a trig identity here. We can remember, all right, what is 2 cosine of theta sine of theta? Well, it's, so v squared over g. 2 cosine of theta sine of theta equals the sine of 2 theta. Sine of 2 theta. All right, so now we have this great expression for p of x at, we could call it second collision. It's the input where we're crashing into the ground right here. So at the end of our trajectory. And now if we know what the x position of our second collision is here, I'm going to scroll down a little bit. Now all we have to do is we have to set this x position equal to distance, because we're now trying to solve for making this be our distance so that we don't just crash in some arbitrary place, but so we specifically crash on, well, maybe we want to hit some target, right? So we want to be setting this collision point equal to distance. So let's do that. We're going to have d, the distance, equals v squared sine of 2 theta divided by g. Okay. Now, what we can do is, let's just say we're trying to solve for theta. If we wanted to solve for theta, well, we can multiply by g, so we get dg, and divide by v squared, and we get that this equals the sine of 2 theta. All right. Now, if we want to solve for theta, we take the arcsin of both sides. We get 2 theta equals the arcsin of dg over v squared. And now if we want to solve for theta, we say that theta equals the arcsin of dg over v squared over 2. The arcsin of the distance times the gravity divided by the square velocity divided by 2. This is the angle up that you have to fire at if you want your projectile to hit where it's meant to hit, at distance away, given the gravity, given how far or how fast your projectile is coming out. If we were to say, apply this to our original problem, let's look at our variables. We had the v equals 10, the v equals 10, the distance is 100, and the gravity is negative 9.8. Well, we can say that in that case, so distance was 100 meters, the velocity was 10 meters per second, the gravity was approximately negative 10 meters per second squared. We can say that theta, let's do it in a red color, we can say that theta would have been the arcsin of distance times gravity, so about negative 10, negative 1,000, divided by the velocity squared, divided by 100, divided by 2. Now, what's really cool about this formula is it will tell you if your problem is impossible. This right here, this is asking for the arcsin of negative 10. There is no real angle that the sine of that angle is negative 10. So in this case, we know it is impossible for a cannonball, a bullet, that's coming out of its source at 10 meters per second at any angle. It is impossible for that to be able to go 100 meters. But let's say we amended this very slightly. Instead of coming out of its source at 10 meters per second, what if we said it came out at 50 meters per second? If it came out at 50 meters per second, now instead of dividing by 100, we're dividing by 50 squared, which is 2,500. So now we're dividing by 2,500. And we can solve this now, get rid of this to make some room. If we're going to solve this, now theta is going to equal the arcsin of negative 10 divided by 25, which is negative 2/5. And this is possible, negative 2/5 over 2. So through this process of finding the quadratic that the projectile's motion corresponds to, through integrating the velocity that we had, we're able to find the time when we hit 0 on the y, plug it into the t, solve for when t had to be equal to distance, plug it in, solve for theta. But this distance equals v squared sine of 2 theta over g. You could use this for whatever you wanted. If you wanted to, given theta, v, and d, solve for the gravity on Earth, this would be a valid way to figure out, hey, what is Earth's gravity? You could fire a projectile at 10 degrees above the ground and calculate the sine of 2 theta, find out, you would test how fast it was coming out, and you would see, okay, how far does it go? And then you could calculate gravity from that. V squared sine 2 theta divided by d would be g. You can see what the velocity coming out is, measuring from g, d, and theta. You could figure out the theta, as we did. So, it's pretty cool. Projectile motion was one of the problems that really got me into physics. Hopefully you find it cool too.